Hi everyone. So I wanted to make a quick video covering one of the important concepts, I guess, from what is this 6.3, the arc length section. What I was thinking I'd do in this video is I'd work this problem here, number 14. The reason I chose 14 is because there's three problems on this homework assignment, and I think the first two one of them we did exactly in class, and the other one we did something similar enough that you'll recognize the trick. So I think the one that will be probably the most challenging for you is number 16 down here. And it turns out that 14 is very similar to 16. So hopefully if I solve 14, the method that I use will help you with the part of 16 that is tricky. So without further ado, if you're trying to find the arc length up here in number 14, what you might notice in number 14, unlike number 16, is that you need to parameterize your curve. So I have y equals something in terms of x, and then I'm told that my x values go from 1 to 2. So what I can do is I can say, all right, let's do the x's first. Let's define x in terms of t to just be equal to t. In other words, this x and these x's here, just think about those as though they were t's. Well, then y is a function of t all of a sudden. Y of t would be equal to t cubed over 3, which I'm going to write as 1/3 t cubed, plus 1 over 4 t, which I'm going to write as 1/4 t to the negative 1 power. And now instead of my x's going between 1 and 2, it's my value of t that goes between 1 and 2. And so with this setup, it fits pretty well into my formula. Maybe I should have written my formula somewhere. Why not right here? The arc length is equal to the integral from the bounds on your values of t, so I'll just write a and b to be generic here, of the square root of something with your variable of integration being a t. And that something kind of comes from your distance formula. It's the change in the x-coordinate as a function of t squared plus the change in your y-coordinate as a function of t squared. So I can take this formula here and I can plug in all these formulas, or all these functions. I got x of t equals t. I need dx dt for my formula. So dx dt is equal to the derivative of t with respect to t. In other words, it's equal to 1. And dy dt is going to be the derivative of my function y here with respect to t. So using the power rule, I bring this 3 down in front. I got 1/3 times 3, which is just 1, t squared. Plus, if I bring that negative 1 down in front, I get negative 1/4 t to the negative 2 power. So here's my derivative of y with respect to t. And then I take these guys and plug them into my formula. So let's see, for arc length, I get that the arc length is equal to the integral from, and it's worth pointing out that these say graph the curve and find its exact length. Whatever. If you want to graph it, you feel free, but don't graph it for my purpose. I don't care if you graph it or not. But I do want you to find the length. So I'm going to integrate from 1 to 2, because those are my bounds on t here. And what I want to integrate is the square root of something, that something being dx dt, which is 1 squared, plus dy dt, which is t squared minus 1/4 t to the negative 2 power squared dt. For these problems, I feel like the setup is kind of half the battle. And then, 49% of the battle is the algebra. Usually the calculus isn't too hard, but the algebra, to get this into a form where you can figure out the derivative of it, that's pretty challenging. Because I don't know what the antiderivative of this mess is. But what I can do is I could expand, and this trick will be very similar to the trick that you do on number 16. I can expand this all out. Think FOIL. So I got the square root of 1 plus, and then t squared minus 1/4 t to the negative 2. If I square that, t squared squared is t to the 4th power. See if, that's not going to let me do this. Try that again. There we go. Just have to write quickly. If I wait too long, it won't let me write underneath the radical. Maybe I'll write out what this is equal to, and then I'll explain why. I get minus 1/2 t to the 0 power plus, I wasn't quick enough. Okay, this sucks. Sorry, try one more time. I'll write really quick this time. 1 plus t to the 4th, it's like a ticking time bomb, minus 1/2 plus 1/16 t to the negative 4th power. All right, I got it in. Now I got to make sure that I didn't screw up my algebra in there. If I were foiling this out, the f in FOIL would be t squared times t squared, which is this t to the 4th. The o in FOIL, I'd multiply these two guys, which I think that's the trickiest part. But t squared times t to the negative 2 power, that's just 1. because t to the negative 2 is 1 over t squared. So when I'm multiplying the t squared times the negative 1/4 t to the negative 2, the t's all cancel out, and I'm left with just negative 1/4. So the O in FOIL would be negative 1/4, but the I in FOIL would also be negative 1/4. So I get negative 2/4, aka negative 1/2 here. And then the L in FOIL is negative 1/4 t to the negative 2 power times negative 1/4 t to the negative 2 power. Negative times negative is positive. 1/4 times 1/4 is 1/16. T to the negative 2 times t to the negative 2 is t to the negative 4. That gets me here. And so you're staring at this thing and you're like, all right, I still don't see how that helps. Well, here's the trick, and I'm going to do the trick in 2 steps. First off, you can combine like terms. So this 1 and this negative 1/2, I could put those together and say that that's positive 1/2. And so, okay, you're probably buying that, but you don't see why that helps. Well, this is a perfect square. You might not recognize this is a perfect square, just like you might not recognize that what you end up with after you do all the algebra up here gives you a perfect square. But trust me, it does. This is a perfect square. You just have to determine what is being squared in there. What I'm saying is if you took t squared and plus 1/4 t to the negative 2 power, and you squared that thing out, if you FOILed it all out, what you would get is exactly what you have on the line above. And that's tricky. The algebraic skills necessary to recognize that what you have right here is a perfect square is tough. And had you not seen an example, like you're seeing one now, it wouldn't really be reasonable for you to expect to see that. But maybe if you were looking for a perfect square here, you might be like, well, there's got to be a t squared here to take care of this one. And there's got to be something t to the negative 2, I guess 1/4, so that when I square it, I get this term. And hey, that works out perfect. That leaves me with this positive 1/2 here. Why is that so good? Because what made this thing so hard to integrate to begin with was this radical, the square root sign. But now I got some stuff being squared, and the square root and the squares I can cancel out here. It's worth pointing out you can't cancel them here. You can't cancel this square and this square root, or this square and this square root, because I have a sum of terms here. But if I just have one thing that's being squared and taking the square root of all of that, I can rewrite this as, I'm pretty low on room here, the integral from 1 to 2 of, and then if the square and the square root cancel out, I'm just left with t squared plus 1/4 t to the negative 2 power dt. I'm done in a sense. You're like, you haven't done any algebra. Yeah, or any calculus. That's true. I spent all my time doing algebra. Guess I should do the calculus because this is a calculus class. But I think really you're done with the hardest part. It's getting into this form. Because now all I got to do, and I'm trying to decide where. I don't know, up here maybe? Sure. I figure out the antiderivative of this guy. So instead of the t squared, I'm going to write 1/3 t cubed. And then instead of the 1/4 t to the negative 2, let's see if I added 1 to this exponent, it would become negative 1. But I got to bring that negative down in front to kind of compensate for that. So I get minus 1/4 t to the negative 1 power. And that thing I want to evaluate from 1 to 2. So to do that, first I'm going to write this expression with 2's in place. So 2 cubed is 8. So I got 8/3. Oh, come on. You can see why I don't like making too many of these videos. Some of these software things drive me crazy. 2 to the negative 1 power is 1/2. And 1/2 times negative 1/4. Oh, come on. All right, just let me write. I'm not going to delete it this time. Gives you this negative 1/8. I should go quicker through this because I know you know how to do this. And then you get 1/3 minus 1/4. What I'm saying is if you plug in 2's and then plug in 1's, I think this is what you get when you plug in 2's. And this is, yeah, this whole thing is what you get when you plug in 2's. This whole thing is what you get when you plug in 1's. And then at this point, you're probably putting it into a calculator, but because I don't have a calculator in front of me, I'm going to call that 64/24 minus 3/24 minus, and then this is 1/12, 4/12 minus 3/12. So this is 61/24 minus 2/24. What I'm saying is I think you get 59/24. Oh, that's pretty illegible. At 5 anyways, as this answer. But really, I'm less concerned about that. I'm sure when you get to this point, you could get the right answer. I trust you that you could do that, and if you couldn't, it wouldn't really reflect on your calculus knowledge. It would be a little algebraic mistake. Where this problem gets tricky is going from this line to this line. And for what it's worth, where 16 is going to get really tricky will be something very similar. So look for that case so that you can simplify your integrand. I think that's what you call that, the thing under, after this integral sign. And then you can take the antiderivative and you can evaluate this thing. So that's all I got for this example. Hopefully that helps people get through all of the homework. I will see you guys on Monday. Have yourselves a good Thanksgiving.